Dear students, thank you for watching and welcome to part 2 lecture video on chapter 3, which is about hypothesis testing. In part 1 lecture video, we have looked at hypothesis testing of population mean when population standard deviation or sigma is known. In this part 2 lecture video, we are going to learn about hypothesis testing of population mean when sigma or population standard deviation is unknown. As well, we'll also learn about hypothesis testing of population proportion. Let's start by dealing with hypothesis testing of population mean when population standard deviation is unknown. T-test is applicable whenever the researcher is drawing a single random sample to test the value of a population mean. The population standard deviation is unknown and the population is normally distributed for the measurement of interest. And the formula the researcher apply for testing hypothesis about population mean when population standard deviation is unknown and the population is normally distributed is this one. T is equal to x bar minus mu all over s divided by square root of n, where t is observed value of t and x bar is sample mean, mu is population mean, s is sample standard deviation, and n is sample size. When we are finding table value of t, it is necessary to know or identify df or degree of freedom, and the degree of freedom is equal to n minus 1 where n is sample size. Let us deal with one case. Students, assume that figures released by USA Department of Agriculture show that the average size of farms has increased since 1914. In 1914, the mean size of a farm was 174 acres. By 1997, the average size was 471 acres. Between those years, the number of farms decreased, but the amount of tillable land remained relatively constant, so now farms are bigger. This trend may be explained in part by the inability of small farmers to compete with the prices and the costs of large-scale operations and to produce a level of income necessary to support the farmer's desired standard of living. Suppose an agribusiness researcher believes that the average size of farms has now increased from 1997 mean figure of 471. To test this notion, she randomly sampled 23 farms across USA and ascertained that the size of each farm from country records. The data she gathered is presented as follows, and let us use a 5% level of significance to test her hypothesis. Let us assume that the number of acres per farm is normally distributed in the population. This is a sample data. So let's begin with the first step. Step number 1 is establishing hypothesis, i.e. null and alternative hypothesis. The researcher's hypothesis is that the average size of USA farm is more than 471. Because of this theory is unproven, it is the alternative hypothesis. On the other hand, the null hypothesis is that the mean is still 471. Therefore, H naught or H sub 0 is mu is equal to 471 and H sub A or HA is mu is greater than 471. The second step or step number 2 is identifying test statistic. Since in this problem population standard deviation is unknown, but population is normally distributed. T statistic is the statistical test that we need to use. Therefore, we use T formula. At step number 3, we need to identify level of significance or alpha. In our problem, we assumed 5% as a level of significance, therefore 0.05 or 5% is alpha. At step number 4, we look at sample data. We are given with sample data. Therefore, degree of freedom is n-1, which is 23 minus 1, which will be 22. Therefore, degree of freedom in our case is 22. And this test is one-tailed because of in alternative hypothesis, the sign is greater than. Therefore, it implies the test is one-tailed test. And the critical table t-value is 1.717. In order to find the critical value or table t-value, we need to have t-distribution, and we look at t-distribution by using level of significance and the degree of freedom. In our case, degree of freedom is 22, level of significance is 0.05. Let us look at this figure or table value of t statistic. Therefore, this is t distribution. In our case, alpha is 0.05, so that we select this column. Degree of freedom in our case is 22. Therefore, we look at 22 here. We look at 22 row is 22 value. Therefore, at the intersection point of 22 and 0.05, we find this value 1.717. Therefore, critical table t value is 1.717. Our decision rule is to reject the null hypothesis if the observed or calculated test statistic is greater than positive 1.717. Step number 5 is gathering data, so that we are given with gathered sample data. Let us proceed to step number 6. Step number 6 is analyzing the data. Therefore, we calculate sample mean, and when we use sample data about 23 data points, sample mean will be 498.78, which means when we add these all figures and when we divide these all figures by their number of observation or by 23, the result will be 498.78. This is how we can calculate sample mean. And sample standard deviation will be 46.96. Therefore, the observed or calculated t-value is t is equal to x bar minus mu all over s divided by square root of n. Let us substitute figures in this formula. X bar is 498.78. So therefore we take here minus population mean is 471 from our hypothesis all over S or sample standard deviation is 46.96. Therefore we take here divided by square root of n in our case is 23. Finally we will get 2.84. This is observed or calculated t-value. At step number 7, the observed t-value of 2.84 is greater than the table t-value of 1.717, which means we compare critical table t-value with observed t-value. Therefore, when we compare these two figures, 1.717 and 2.84, we find that the observed value or 2.84 is greater than the critical value, which is 1.717. Therefore, the business researcher rejects the null hypothesis. Rather, she accepts an alternative hypothesis and concludes that the average size of a USA farm is no more than 471. And we can also show this hypothesis test or analysis diagrammatically as follows. The critical t-value is 1.717. Therefore, whenever we obtain observed value greater than 1.717, we are going to reject the null hypothesis at 0.05 level of significance. But if the observed t-value is less than 1.717, we are going to, accept the null hypothesis. Therefore, by this way, we can show rejection region and the null rejection region. In our case, the observed or calculated t value is 2.84, which is in rejection region because of it is greater than 1.717. Therefore, we need to reject the null hypothesis. The final step is taking a business decision. Therefore, the agribusiness researchers can predict about what it means to have larger farms. If the average size of a farm has increased from 471 to almost 500, it may represent a substantive increase. So that could mean that small farms are not financially viable. It may also mean that corporations are buying out small farmers and that large company farms are on the increase. Such a trend may spark legislative movements to protect the small farmers, or it also implies that larger farm sizes may also affect commodity trading. This is how we can present the business implication of hypothesis tests. Therefore, when population standard deviation is unknown, t-test is the fair test, and we can test the hypothesis by working through 8 steps. Our last lesson in this chapter is hypothesis testing of a proportion. Data analysis used in business decision making usually contains proportions to describe aspects such as market share, consumer makeup, quality defects, on-time delivery rates, profitability stocks, and others. Therefore, to test the hypothesis about a proportion, the sample size must be large enough, i.e., n times p must be greater than or equal to 5, as well n times q must be greater than or equal to 5. When n times p and n times q are greater than or equal to 5, we use the formula of z is equal to p naught minus p all over square root of p times q divided by n, where p naught is sample proportion, p is population proportion, and the q is calculated as 1 minus p. Therefore, in order to test the hypothesis about a proportion, whenever sample size is large, z statistic is appropriate test statistic. Let us look at one example in order to be familiar with how hypothesis about population proportion is tested. Let us assume that a survey of the morning beverage market shows that the primary breakfast beverage for 70% of Americans is milk. A milk producer in Wisconsin, where milk is plentiful, believes the figure is safe for Wisconsin. To test this idea, the researcher contacts a random sample of 515 Wisconsin residents and asks which primary beverage they consumed for breakfast that day. Suppose that 115 replied that milk was the primary beverage. Using a level of significance of 0.05, let us test the idea that the milk figure is higher for Wisconsin. we are going to test this hypothesis by working through HTAB system of hypothesis testing. Therefore, the first step is establishing a null and alternative hypothesis. The milk producers theory is that the proportion of Wisconsin residents who drink milk for breakfast is higher than the national proportion, which is the alternative hypothesis. Therefore, the null hypothesis is that the proportion in Wisconsin does not differ from the national average. Therefore, H naught ASP is equal to 0.17 and HA ASP is greater than 0.17. At step number 2, we need to identify test statistic. Therefore, in order to test a proper hypothesis about population proportion where n times p and n times q are greater than, here 5 is the statistics. Therefore, the statistic is used here, and we use this formula in order to obtain observed or calculated z value. Step number 3 is identifying the type 1 error rates or level of significance. We are testing the hypothesis at 5% level of significance. Therefore, alpha or level of significance is 0.05. Then the next step is identifying the type of test. Our test is one-tailed test because of in alternative hypothesis the sign is greater than. And the test is only, the test will be two-tailed test only when in alternative hypothesis the sign is not equal. But whenever the sign in alternative hypothesis is either greater than or less than, the type of test is one-tailed test. Therefore, in our problem, type of test is one-tailed test. And let us find the table value. Alpha is 0.05. Therefore, when we deduct 0.05 from 0.5, which is the probability of one tail, we find 0.4950. Therefore, when we find, when we look at this probability in the Z distribution, that value will be 1.645. The sample result must yield an observed Z value greater than this amount, 1.645, for the milk producer to reject the null hypothesis. In diagram, we can show the rejection and the null rejection region of this problem as follows. Population proportion is 0.17. At 0.17 or population proportion, Z is 0. And we are testing the hypothesis at level of significance of 0.5, 0.05 or 5%. Therefore, the critical Z value is 1.645. Therefore, if we find the observed Z value greater than 1.645, we are going to reject the null hypothesis. Therefore, this region is rejection region. But if the observed Z value is less than 1.645, we are going to accept null hypothesis. Therefore, this region is null rejection region. We will not reject the null hypothesis. This is how we can show our problem in diagram. The next step is gathering data and calculating some statistical values. In our case, n is 550 and x is 115. Or the number of items that uses milk as their primary breakfast beverage. Therefore, sample proportion is calculated by dividing x by n. Therefore, P naught is equal to x over n. X in our case is 115, or those individuals who prefer milk as their primary beverage for their breakfast, divided by total overall sample size, which is 515. Therefore, finally we will get 0.209. This is sample proportion. Therefore, step number 6 is calculating observed value of Z. Therefore, the observed value of z is equal to p naught minus p divided by square root of p times q all over n. Let us substitute these figures in this formula. P naught in our case is 0.209 minus p in our case is 0.17 divided by square root of p is 0.17. Q is 0.83, which is 1 minus 0.17 divided by, so I mean to say 550, which is sample size. Finally, we will get 2.44. And the 2.44 is in rejection region because of it is greater than critical value of z, which is 1.645. Therefore, the null hypothesis is rejected. Because of z, which is 2.44, is beyond critical value of z at 0.05 alpha, which is 1.645. This is in the rejection region. Therefore, the milk producer rejects the null hypothesis. The probability of obtaining z greater than or equal to 2.44 by chance is 0.0073. Because of this probability is less than alpha, which is 0.05, the null hypothesis also rejected. Therefore, our test results shows, or it implies, that the null hypothesis should be rejected. The final step is, taking or presenting a business implication. Therefore, if the proportion of residents who drink milk for breakfast is higher in Wisconsin than in other parts of the U.S., milk producers may have a market opportunity in Wisconsin that is not available in other parts of the country. This is how we can state the business implications for this hypothesis test. This is how we can test hypothesis about population proportion by using Z statistic. Thank you very much for your attention and for your time. And this is all about lecture video on chapter 3, i.e. on hypothesis testing. Have a nice time and have a nice study time. Thank you.